other thing is we can actually count how far back in time we're going because you can count each ring. So again, this proxy data has to tell me two things. One, it needs to tell me about the climate, and two, it needs to tell me about the time. So in this one, these rings are so close together that somebody used a microscope to count them for us, and they're telling us that if I counted from the outside to here, that's 550 rings. And then I could keep counting and I'd find out that this tree is about 598 years old. So if I cut this tree down today, and I was counting it, then this is the year 2016, and I would count back, that's 550 years ago, 551 years ago, 552 years ago, 553 years ago. Make sense?
Yeah.
So I could estimate when this climate changed. Can you see that these rings are all thin, 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 thin?
Yeah.
Thin, 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 thin. And right here is where they switch from being thin to being thick. Can you see it?
Yeah.
So I know that this year right here is where the climate changed and it became wetter. These are wetter years where the tree grew more, and these are drier. Make sense? So there's some cool stuff we can find out from tree rings that's a little more specific. One, instead of looking at like the last 10,000 years, we're only looking at the last 600 years. And there's good things and bad things about that. So a good thing is we can be really specific. I know exactly what year this was. But the bad thing is I can't go as far back in time because this tree only lived 600 years, and so I can't go any further back than that. Does that make sense? So tree rings can tell us how old the tree is because each ring is 1 year. If it was cut down today, we could count back and figure out what year it was planted. And it can tell us when it was good growing conditions and when it was bad, because the thick rings mean it was good, and the thin rings mean it was bad. Any questions about tree rings?
Are there specific trees you can look up?
Yeah, so all trees have rings in them, but some trees are easier to see the rings. And the ones that we find the most useful are the redwood trees that grow in the California forests. And the reason that we like those trees is because they've been there for a very long time without being cut down. And so we tend to use those instead of smaller trees because they haven't lived as long. One other thing people ask all the time is, Ms. Egas, isn't it bad to go cut down a tree to study the tree rings?
Yes.
Yeah, we're not trying to kill the tree to study the tree rings. So they actually have a tool. And it's a lot like a corkscrew or like a little tiny drill. And they can drill a core sample out of the tree and pull out this little skinny strip so they can see the stripes and the layers all the way to the center of the tree without actually hurting or killing the tree. They just put a little putty over the hole when they're done so bugs can't get in there. And they can study the tree rings without cutting the whole tree down. Does that make sense? Alright, so that was the third of 5. And just so you know, if you want a C on your summative, you're going to tell me about 3 different types of proxy data. So maybe tree rings, lake cores, and deep sea sediments are the 3 you tell me about. But if you want a B or an A, you're going to need to know about these last 2. Back on the slide.
Tree rings. The ones that says rings close together, yellow.
Rings close together, which is thin rings, are drier weather. And rings farther apart, thick rings, are wetter. Does that logically make sense to you? A tree gets more water, it grows fatter.
How does it grow fat?
So trees use the carbon dioxide in the air and the water to combine and make their tree stuff. Like the cellulose they're actually made of is built out of those things, right? And so if they get more water, they can build more tree.
Oh.
Just like if I eat more food, I get fatter, right? Same idea. Okay, So carbonate is a mineral that forms in soils, and you can find it all around the world. And it looks a lot like baking soda. So this white powdery stuff right here is the carbonate that you find in the soil. So can you see, like, this is the grass at the top, and then this is dirt underneath, and then what is that, like 7 inches down or something? You see this stripe of carbonate in the soil. And the reason that happens in a stripe like that is because the rain washes down through the soil, and it washes this mineral down to this level, and the amount of rain you get will determine like how far down this gets pushed. But this is basically like where the rain kind of stopped, and this mineral started to pile up and make a big stripe in the soil. Can you see it? So that mineral right there, that carbonate, is useful for us. It can tell us about the climate, but it can't tell us about the climate by itself. We have to do a lot of work to it in order to make it tell us about the climate. So that mineral is called carbonate, and when you break it down, it turns into carbon dioxide. Everyone do this in your hand. That's carbon dioxide. Don't smell your breath. Just go like this. That's carbon dioxide. And that molecule, carbon dioxide, is made of 1 carbon atom, that's the black part in the middle, and 2 oxygen atoms, that's the oxygen on the outside. And the reason that that's useful to us is because we can look at the isotopes and figure out what the climate was like. So just to review, isotopes are different forms of the same atom, but are heavier or lighter. So this is carbon 12, carbon 13, and carbon 14. They're all carbon. They act the same. The only difference is this carbon has 6 neutrons, and this carbon has 8 neutrons, and therefore this carbon is heavier. So I want you to picture something with me. If I had 2 different balls, and one was heavier than the other, which one would be easier to throw? The light one. Why? It's lighter. It takes less energy to make it move, right? So when we look at these isotopes, carbon 14 is heavier. It took more energy to make carbon 14 than it does to make carbon 12 because it's heavier. It just took more energy to make it. Does that make sense to you? So what has more energy? Are you getting more energy from the sun on a hot day or a cold day?
Hot day.
A hot day has more thermal energy from the sun. Does that make sense to you? Okay, so heavier isotopes form when it's hotter because there's more energy from the sun allowing them to get built. Does that make sense to you? So isotopes are really useful to us because when we look at them, we can figure out if I find more heavy isotopes, that tells me it was warmer because it took more energy to make that isotope. So the climate had to have been warmer in order to make heavier isotopes, okay? So the whole idea here is we measure how heavy these isotopes are, and then if we find that there was a bunch of heavy ones, then we know it was warmer, and if there's a bunch of light ones, we know it was colder. And they've been doing this for so long, and they're so good at it, that we actually we have a scale. We know that if you find this many of this heavy, it was 76 degrees. Like, we know exactly how warm it was because we've done it so many times. So this guy we met on the field trip. His name is Andy. You didn't meet this guy. He doesn't work there anymore. But this was the vacuum line. And so I want to remind you that we started with this white dust out of the dirt, right? So we collected this white dust. It's called carbonate.
Hold on.
And we need to analyze it in a machine to find out how many of the atoms are heavy and how many of the atoms are light. But you can't just put dirt in a really fancy science machine. So they put it through these chain of reactions to turn it into like a clean, pure sample of carbon dioxide, just like this. That's our clean, pure sample of carbon dioxide. And so that's what this is is all about is cleaning up that dirt and turning it into carbon dioxide. And then they put it in this machine, the mass spectrometer. And what this machine does is it takes all of the carbon dioxide atoms and it shoots them down this tunnel. And then there's a magnet here. And the magnet basically pushes on each atom. Push, push, push. So if you're all lined up and walking past me and I'm pushing you all, who's going to move farther, a light person or a heavy person? Light person. If I push you and you're smaller, you're going to go further, right? And if I push you and you're heavier, you'll just maybe stay right here. Does that make sense? So when this machine pushes on each atom, the heavier ones are going to not go as far, and the lighter ones are going to move further. So it's a really fancy way to separate out the heavy and light atoms and count them. Because if we know, so then we'll get a graph like this. What happened to my mouse? There it is. So this means there was a bunch of light isotopes, and this was a bunch of heavy ones. Which do we have more of? We have more of this, and I just said that was the heavy one. So this would tell us that we had more heavy isotopes. Does that mean it's warmer or colder? Please stop. That's really, 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 really not cool.
It was warmer.
Warmer, because it takes more energy from the sun to create heavier isotopes. Understand? So an important thing to understand is that isotopes are what we're measuring out of the dirt. Heavier isotopes tell us it was warmer. Lighter isotopes tell us it was colder. And we know when those isotopes happen because, again, we collect the dirt out of these layers. So this is a really giant cliff in eastern Washington. It's an area called the Palouse, and it's over in Tri-Cities. Does anyone know Tri-Cities area? So this is what it's like over there. And you might go out and drill a core sample here, but you don't have to. And the reason you don't have to is because they took a giant machine and cut this hillside to make a road. So down here at the bottom is a road. And so they basically have a core sample right here on the side of this mountain. So they can go there and collect little samples and measure how deep down they are. And they can tell how old they are, because the deeper they go, the older it gets. Does that make sense? So this site is really useful for people to collect their carbonate samples because it's these layers of land that are exposed. We can see them, but they're still all in the right order. So we know that the deeper we go, the older they are. Does that make sense? Okay, we got one more to study, and that's ice cores.
Ooh, I need to write that down.
DJ didn't do the pencil this week. Class number 23. So not forget. Okay. Ice cores. Ice cores are another way we study past climates. You need to get the ice from a place where the ice has not melted before. So you can't just like go out there in the middle of the winter and collect some snow and study that. You need an ice core which looks like this, and you would get it from a place that looks like this, where you again drill down into the ground and collect an ice sample. So see all this snow?
No.
When summertime comes and this snow doesn't melt because this is in the middle of the North Pole and it snows again, this is going to get buried, right? And then the next year it's going to get buried even more. And the next year, buried even more. So ice cores form from snow that falls year after year and never melts. And there's places on our planet where we have ice that goes back 400,000 years. So ice cores are really useful to us because they have the oldest data.